Yeah, thank you, Raymond. And first, I want to thank the organizers for inviting me, and I'm really happy to be here. I was here last week. It was very interesting to hear all the talks. It was mostly about interactive communication, so I learned a lot. So today, since I felt the nature of this workshop is kind of overlap or intersection between CS and information theory, so I thought I'd talk about some work I've done on secure distributed storage and some connections to secret sharing and maybe some new problems related to secret sharing that are motivated by distributed storage. So one thing, I'm going to assume very high level, maybe knowledge of, very, very high level of distributed storage, but if there's something that you don't understand, just please make sure to stop me. And so first, I'm going to start by a little bit of definition of secret sharing. If you know it, just bear with me. But I think that was started first by the famous paper by Shamir in '79. The paper was called How to Share a Secret. As in our community, information theory community, we know also a similar paper or very related topic, which is the wiretap channel of type 2, which is by Ozarov and Weiner. I think it was '82. But anyway, so let me tell you the setting. So first you have a dealer here that has a secret. So think of a secret as a certain number of bits or a symbol or a certain amount of information. And the secret is in the safe. And the dealer want to give keys to the safe to 4 parties here. So this is going to be a running example for this talk, 4 parties, such that any 2 parties can open the safe and get the secret, but any single party cannot know anything about the secret. Okay? So any 2 guys should be able to know the secret. 1 guy should not be able to know anything about the secret. And the question is how to do it. And Shamir's scheme, usually it's explained as in terms of polynomial evaluation, but I like to explain it as kind of a Reed-Solomon code. So what you have to do is, in general, you would have n parties, and k keys should open the safe and know the secret. So you have to mix. So it turns out that assuming that each share is 1 symbol, so you can store a secret of size k minus L symbols. So don't get caught up with the definition of what is k minus L. So the main idea here is that you have to mix the secret with random keys, random symbols that are chosen independently of the secret, and store them on the shares. So for this simple example here, what you do is, so S is the secret, so you kind of mix it with a key that is independent of the secret, and you store key, S plus 2k, and S plus 3k, and you can check that a user that is interested in knowing the secret, all he has to download is 2 shares, and he can decode the secret, and also he'll be able to decode the keys here, but we'll talk about this later, okay? And in general, beyond the simple example, if you have nk, so n shares, k out of them should open the secret, but there's a third parameter, which is L, meaning how about if I have less than the threshold k, so L of these shares should not be able to know anything about the secret. So this is how you define a threshold secret sharing scheme. So in general, for a threshold secret sharing scheme, the construction is very easy, and most of the work in secret sharing literature is about something called the general access structure. So meaning that I don't give you a threshold, but I give you explicitly what set of among these shares should be able to open the safe and know the secret, and what subset of these shares should know nothing about the secret. And there you'll have very interesting stuff. But in this talk, I'm going to focus on secret sharing, on threshold secret sharing, and even for this simple, kind of very tractable secret sharing scheme, I'm going to show it to you, I'm hopefully convince you that there are interesting questions that you can ask in the setting of distributed storage. Should I be standing here? So, but first, I want to make sure that we're all at the same level. So, any questions here? Okay. So now, what is the problem? If threshold secret sharing is easy and we can construct it using mixing keys with secret using random Van der Waals matrix, so what is the problem? The problem is, for me, I'm going to think of these shares as stored on nodes in a network or disk in a data center, for example. And for, as you've heard of this, is that in this setting, nodes will fail with a high probability. So you always have to deal with node failures. So for example, think of these shares as stored on disk, right? And suppose you lose 1 share, right? Now you need to reproduce the share on another disk to bring the system to have the same system again. So this is known as repairing, as the repair process. So we're trying to repair the share. So how would you repair it here? Well, you can think of this. You can download 2 other shares and decode the secret and re-encode it again. So here you decode the secret and the key, and you re-encode it again. Okay? So you recover K. But what is the problem? The problem is you lost security. Why? Because you already revealed the secret to this guy. So this guy can now open the safe. Although you wanted to forbid this, right? So while repairing the shares, you broke the security of the system. And this is the problem that comes from the dynamic of the storage system. So you start by something that you think is secure, and it is secure, but then once a failure happens or a participant leaves the system and you're trying to replace it, you break the security. And the question that I want to ask here, how can I repair a share without breaking the security of the system, and how much is it going to cost me? Here, it's not clear if it's even possible, right, in this small example. So in general, my talk is going to be divided into 2 parts. The first part, which I'm just following Shamir's original title, is which I call How to Repair a Secret. And there, it's going to be some work that I did in the previous year with many co-authors, so I'll mention them when I mention the results. And there will be 2 takeaways in that part. And the second part, which is a recent work that we submitted to ISIT this year, which I call here How to Deliver a Secret, meaning I will worry about what's the communication cost of delivering the secret to the user, and there will be 1 takeaway. So the majority of the time I'll try to spend it here and a little bit here, okay? So now I want to go back to this problem, which is the first part, which is how to repair a secret. So now if you think of it, why the security is broken here? So the first thing that you think about is that maybe you're revealing too much to the participant, to the share, right? And this is why the share can decode the secret. So you don't want to reveal too much. You want to reveal just what is necessary for the share to decode, but not know the secret. And is this possible? And actually, we know that this is possible based on the theory of regenerated code and distributed storage systems, because we know that we can repair a coded part without downloading the whole thing, right? So let's try to do this. So using the work of Demakis et al., we know that in this setting, I can repair a coded part in the Reed-Solomon code by downloading, actually, instead of downloading everything, the whole file, which is 2 units, I can do it with downloading 1.5, as long as I connect to 3 parties instead of 2. So meaning I download half a unit on each one. So what I can do here is that use a regenerating code and mix it with keys. Yes?
Are you going to be focusing on exact repair or functional repair?
Yes, I'm going to focus on exact repair, yes. Exactly. Yes, exactly, yeah. But that's a good question. So I'll mention a little bit. Yeah, function is still open. So here's what I'm going to do. So don't worry about the code itself. So what I'm doing here, I'm using a regenerating code that allows, yes?
Could you explain what regenerating code is first?
Yeah, sure. So here's an example maybe. So it's regenerating code. So here, if you think of this code, Reed-Solomon code, where is it? So I think Kenneth is going to talk about it, and Xiaotian is going to talk about it in their talk, but very quickly. So here, if you lose 1 coded part, so here, think of your information as S and K, but if you lose 1 coded part, which is K, how would you reproduce K here by talking to the other nodes in the system? One way to do it is that to decode everything, so talk to 2, because K is 2 here, and download everything and decode S and K, but you only want K, so you throw away S. And it turns out that you don't need to download everything, but you have to connect to more nodes in the system, right? So the thing here is that because I only want K, you can prove information theoretically that if I connect to more nodes in the system, I don't have to download S and K. I can download less and still recover K, and this is how you do it. I think Vijay will also talk about this, maybe, yeah. So it's a little bit more complicated, but if you do this, right? So here, S is the secret, and I divide my keys into 2 parts, K1 and K2, and now I connect to 3 parties. And you see here, I can download only half a symbol from each, and you can decode what you just lost here. Okay? I mean, it takes time to parse the code, but I mean, this is the general idea, is that you don't need to download everything to decode a coded part. Yes?
One last question. So with the repair messages, you're still going to have the requirement that the conditional entropy of the secret will be the entropy of the secret given all of the repair messages.
The conditional
So
entropy.
is he not going to learn anything about the
Yes, exactly. So what you do is that you use the key in a smart way. So if you take a regenerated code as it is, it's going to be tricky. So here, I did something extra. I'll tell you what's extra in 2 slides probably. But yeah, you're right. So you want to make sure that you hide also what you're downloading from him. So these keys, I'm using a little bit extra keys here. Actually, you see I have K1, K2, K3. To hide also from this guy. And in this case, you can store a key of size half a symbol. So in general, what you can store, so 2 shares should open the safe and know the key. So the key using the classical secret sharing could be only of size 1. But here, because of repair, it goes down to 0.5 because you have to pay for this. Okay? Yes? I'm sorry? Oh, you're right. You're right. Yes, yes. Thank you. Yes.
And what's
Yeah.
the idea behind introducing the additional blue keys?
Oh, so the theory, if you do the cut-set bounds, the information theory, it tells you that you can do it by downloading half a symbol. So this is maybe a very high-level answer. So then you need the granularity to be able to do it. And for this, you need to store 2 symbols on each. Can you repeat? If this does not answer your question, can you ask it again so I can try to answer it? Okay. So to answer your question, so what I'm doing here, if you think the general mentality of or general argument, what I'm doing here is trying to build a secret sharing code by doing 2-step. It's kind of a separation scheme. First, I have a regenerating code, which is a minimum storage code. So again, there will be lots of talk on this. And on top of it, and this is the smart thing that I have to do, I have to mix it with key. And if you're not careful about how you mix it with key, the security can be broken by this guy. So you have to use something called maximum rank distance regenerate codes. So you have to use MRD codes. Think of it, if you don't know what these are, again, you can think of them as black boxes. But you need to first make sure the system is secure by mixing the secret with keys, and then use the regenerating code that makes sure that when you repair, you don't download too much. Okay? Yes?
Is it proven to be optimal to divide this into 2 steps?
This is the first takeaway. So the first takeaway message is that if you do this, it's not optimal. So separation is not optimal. So what am I doing here? This scheme means that, well, let me minimize the bandwidth, what I'm revealing to this guy. Use the best regenerated code that minimizes the bandwidth. So here, there's no way you can repair this code by revealing less than 1.5. So that's what information theory tells. So if I do this, and I use keys on top, this is not optimal. And this is the trick. This is what makes the security problem interesting and a little bit more tricky than the non-secure part. Now, why? Yes?
You say you use minimum repair bandwidth, but then you use a minimum storage code.
So to minimize the repair bandwidth for that code.
You use a minimum storage code.
So maybe let me. Yeah.
So sorry.
Yes.
So in that schema, the flipping a coin or how?
Here, yeah. The coin flipping is here.
Yes, but to the coordinate, it looks like they need to know each other's coin flip, is that right? Or they have to do side communication or?
Who?
Well,
The nodes?
If you go back to the previous slides.
Yeah.
No, party 3 and party 4, they're like flipping a coin, right?
Oh no. So the guy who flips the coin is the dealer. So he flips the coin. He stores these things and then he leaves.
Oh, I see. So then it automatically they get either. I see. So okay.
Yeah. So I mean, if the dealer is always there, then there's no problem. Then the dealer can give the party.
So that's how they coordinate, so to speak.
Yeah.
Zeros and ones. Okay.
Okay, so first I want to give you some intuition. Maybe this answers Ivan's question about what these codes are. What is the intuition that separation is not optimal, right? So I want to give you an example, and hopefully the example can build the intuition. So I'm still considering the same problem, the 4-2 secret sharing problem. Again, so I'm running with an example, but all these, in general, it's an NKL secret sharing. So here's I'm going to construct a scheme that does better than the previous separation-based scheme. So instead of storing a secret of size half, I'm going to be able to store a secret of size 2/3. So first, I'm going to use Shamir's old scheme, or classical scheme, for this to generate a secret share for these parameters, 6, 5, and L equal to 3. Now, why I did this, you'll see it in a second. So this is unrelated to what I'm doing for my system. So what does this mean? So I have a secret of size 2. So each symbol is 1/3, think of it. And then I encode it into 6 shares, such that 5 should be able to give you the secret, but any 3 tells you nothing about the secret, okay? And we know how to do this. Now, how is this going to help me? Then I'm going to use a code that was done by Vijay's group called, in the language of storage, called minimum bandwidth regenerating codes, MBR codes. But this is what I'm going to do. So I'm going to take these 1/3, 1/3, 1/3 shares. I'm going to distribute them on the system in this following way. So 1, 2, 3 here, and 1, 1, and 1, 2, 3 here, 4, 5, 2, no, 4, 5, 4, 5, and 6, 6 in this way, right? So what are these? These are the shares that come from this classical secret share. Now I claim that this is a secret share that can repair and store 2/3, a secret of size 2/3. Why? If you check it for a second, suppose you lose this part, right? So you lost 1, 2, 3. How would you reproduce it? You would download 1 from here, 2 from here, and 3 from here, okay? Now, why this guy did not know the secret? Because these things are coming from a secret sharing scheme with L equal to 3. Meaning, if you observe any 3, you know nothing about the secret. You look like you're bothered by something, so I want to...
What do you mean a secret of size 2/3? I'm just.
Oh, okay, so you multiply everything by 3. So, yeah.
Okay.
Yeah, my problem is that I want to normalize the share size to 1. So I want to, all the time, each share to be 1. So if you're bothered by 1/3, multiply everything by 3.
Okay, so what you're doing is storing 2 secrets.
Yeah.
And you want to make sure that nobody knows anything but you.
Yes, and yeah, exactly. So here, instead of having share size 1, it's 3. Yeah, yeah. I know, it's puzzling. But feel free, if there's something that is bothering you, just tell me. But does it make sense why is it secure at least? So you want to ask something? So because you started from classical secret sharing scheme that guarantees that any 3 doesn't leave this, doesn't reveal anything about the secret. And here, this is why, in this scheme, you reveal nothing, okay? So what's going on here? So what is the intuition? How come separation? I'm doing the best thing when I'm doing separation. Because I'm minimizing the bandwidth. So why this does better? Because at some high level, if you want, the size of the secret you can store is equal to the amount of information on K shares minus the amount of information you download. So what we did previously, we used a Reed-Solomon code which maximizes the information on K disk, right? But then if you maximize the information on K disk, you pay a hit on the bandwidth. So you have to download a lot. Maybe if you say, well, I'm going to store less, right? But then if you store less, you download less, but the overall size of the secret is more. So there's this tension between how much should I store and how much should I download. And what we did before is that we said, oh, let me use all the storage. Use the storage in the most optimal way. But then you have to download a lot. And then if you say, well, let me not use all the storage, then you have to download less and you can actually store a higher secret size. Yes?
So to repair this node there, you need two-way communication between the node and the guy.
In what sense?
In the sense that it's not always that I have to take one from the second.
Oh yeah. So he can just tell them that I'm the guy who's repairing node 1, which was node 1.
Don't care that.
Because this is log n bits and this is Right, so think of these as terabytes versus I don't know. If you have a system with 100 bits.
It's more a security question than I know who's getting corrupted somehow, but I don't care.
Here I don't care, but I don't know if I should care. Yeah, I haven't thought of it. Yeah, but I just care about the content of the information. I don't want to reveal the content of the information. Yes.
So you have
Oh yeah,
They
so
would have
so L is less than K. So if we go back to the safe, right? Maybe this is the easiest conceptual way to understand. So you want, let's say you have a 10, let's say 7, 3. So let's say this is NKD.
D is what? That was
I'm sorry?
What's D? D's not.
Oh, L. I'm sorry, L.
L?
Yeah, yeah. We will have D.
Here you have L equals 3, which is bigger than K equals 2. Is that
Yeah. So here K equal to.
That seems fine because L is smaller than K.
Yeah, yeah. Here also L is smaller than K.
Oh, I see. Oh, so it's a different K.
Yeah. So here I have two systems. So this is my goal, right? To construct this. But to construct this, I needed to construct this first. And why I did this? Because this is the classical secret sharing, which we don't know how to repair, or I'm trying to repair, right? So here I don't care about repair. But I'm saying, if I want to do repair, I can construct a classical one and then build a new one from it that I can repair. So this is the general problem that I'm interested in. So given N, K, D, and L, what is the maximum secret size that I can store? We call it secrecy capacity, right? So the problem is very hard. So, and it's still in general open, especially except for certain cases, which I'm going to tell you what cases. But I'm going to tell you first how we start thinking of it. So first, because it's just a little bit of a, we thought if we put more structure to the problem, maybe we can say something. And the structure that we thought of putting is that putting some constraint on how much you download. So in the problem that, as I defined it so far, you're free to do whatever you want in terms of download, but you have to pay for it. If you download more, you may reveal more to the eavesdropper, and you might then have to take a hit on the secret size. So here I say I'm only allowed to download that much of information, which we call it beta amount of information on each link. So here, so I give you in addition this constraint, how much you download. Then we can show that the secret size cannot be more than this. So I'm not going to spend time on parsing this, but you're going to lose L units of secret because they have L shares that are collaborating, and you have to lose more because there will be some overlap between the data on the nodes. But anyway, and I know this is a fundamental, these 2 weeks about fundamentals and information theory, but I'm going to skip the proof because the proof is kind of, and I'm sure that the talks on storage are going to go through this. It's a standard proof in distributed storage where you transform the problem into a network, and then you look at the cuts in the network, into a multicast network, and you look at cuts in the multicast network. So don't worry much about this. I'm sure if you come to the other talks, you'll know about it.
That's a proof that's needed for a functional repair.
Yes, exactly, yeah.
Say you only work
Yeah,
with-
yeah, and this is an upper bound,
Yeah.
right? So,
You use a shorter proof in this case. You don't need.
yes, yeah, that's true. But even for functional, so I don't want to confuse people between functional and exact, but yeah, this is all, even for functional, you cannot do better than this. So if you don't know what functional is, functional meaning that I want to repair this, but I don't care that it's exactly this. What I care is that the system is always an NK secret sharing system. So that's what functional means. You don't want to repair the exact data, but you want to keep the functionality of the system. And it turns out this bound, you can achieve it. But then you can achieve it for what beta? For what constraint on the download? For if beta is equal to 1 over d. So I apologize for the notation. So d is how many? So you have 1 to n, and you have a share that is lost. D is how many shares you contact to repair. So I have now n, k, d, and l. So yeah. Now, usually you want to repair by talking, maybe you want to repair by talking to n minus 1, meaning everything except the guy who failed, but maybe not all the nodes are available, so this is an additional parameter, right? And it turns out that the scheme that I showed you achieves it. The generalization of it, and for d equal to n minus 1, and for d less than n minus 1, then there are codes called product matrix, again by Vijay's group, that also you can achieve. So. Again, so if I'm saying something that you cannot follow, we can talk offline, or you feel free to ask me. Because there are lots of things that I'm borrowing from the theory of regenerating code, and I assume that I'm not the first talk, but yeah, but at least I want the concepts to be, at least I can convey the concept, so that you know that such a problem exists and such result can be solved, and these are the open problems in that area. So I hope I can convey this. Now, so what I proved, where is it? So yeah, so if I go back to my running example, so what I proved is that if you allow me to download one symbol to repair, then actually this is the best thing. So I showed that separation is not optimal. I showed that this scheme can store 2/3 is a secret of size 2/3, or two secrets, right? And now using this theorem, we can show that in this case, this is the best thing you can do. If the bandwidth is 1/3. And the question is, what if you allow me, in this case, in this example that I started with, if you allow me to download whatever I want, there's no constraint on the bandwidth, can I do better than this? So here for b equal to 1/3, what if I give you b equal to 1/2, or I give you infinite bandwidth? What should you do? It turns out that in this case, even if I give you infinite bandwidth, even if bandwidth is free, you should only download that much. Because if you download more, you're going to review more, and you're going to take a hit on your secret size. And this is a work by Tandon et al. That showed that, so I'm back now to the unconstrained secret, the problem of repairing a secret with no constraint on the bandwidth. It turns out that what we did so far is optimal for two cases. For n-1, meaning k equal to n-1, or n2. So you should be able to open the secret by having all the keys except one, or only two keys. In these two cases, what I did so far is optimal. But in both these, L is equal to k-1. So this is called perfect signature. So, and beyond this, the problem is open. Okay, and the proof is information theoretical here. So you have to basically use information theory and basically Shannon inequalities to bound how much these shares that are happening in this node know about this share. So you want to bound this kind of overlap of information. Because this guy needs to have this guy if this guy fails, so it must know something about what he stores. And you try to bound this. I'm not going to go through the proof, but again, I can do it offline. Maybe mainly the proof is mainly knowing how to manipulate this, and maybe the only, non-familiar, for me at least it was, ingredient in the proof is Hans inequality. So maybe for you it's something you know, but this is the only piece that is usually, I don't see it in many proofs, is Hans inequality. Basically to average what's happening between all of them. But anyway, okay?
Go 2 seconds back
Yeah?
for that download result.
This one?
Yeah.
Yeah. So this means that the scheme of first using Shamir's and then distributing it, or using product matrix, is optimal in this case, even if there's no constraint on the bandwidth. And the proof is information theoretical. So I want to talk a little bit, just to summarize this part. So in general, the problem is open, and we know that is solved, again, for L equal to k-1, and for k equal to 2. And otherwise, the problem is open still. So other open problems is that what would happen if we have functional repair? So functional repair, you may have hope to do better than this. Functional, as I said, you don't want to repair exactly the share, but you want to keep the system an NK system. Also, you might ask the question about what happens if these shares are malicious and they change and corrupt their shares. So what would happen there? So we had some work on this. The last question, which I want to try to answer next, is that, okay, so the problem is open, but we know that we have a scheme, which is the separation scheme, right? How bad is that, right? If I just want to do regenerating code and then MRD code on top, is it too bad? How far I am from optimal? So that's what I want to try to answer next. So I'm going back to the separation scheme. So here, I want to stick to what I call NK-MDS code, meaning Shamir scheme, and then I will try to repair it. So forget about these kind of other constructions. So it turns out that it's kind of not a very good idea, and it's kind of a negative result maybe. And why is that? So if you didn't want to repair, then the secret size is k minus L. That's how many secret you can, that's the size of the secret you can store using Shamir scheme. Okay? Now, if you want to repair Shamir scheme as it is, then the secret drops down to this. You have this multiplicative factor that decreases exponentially with L. And which is, for me, it's very surprising because this is the first time, or not the first time, I don't know, the first time where the secrecy capacity decreases exponentially with the number of nodes that an eavesdropper looks at, or shares that they collude together. Okay. Now, just maybe this is hard to see what is going on. So let's focus on the case of n equal to k plus 2. So k equal n minus 2. In this case, this would be the size. So I'm just applying the previous bound to the special case of k equal to n minus 2. So this multiplicative factor becomes 1 over 2 to the L. So this is the price to pay to repair this, the secret. Now what does this mean? Actually, so I'm hiding the details. What does this mean? That every time, where is this coming from? So every time it turns out that a share is helping another share, it has to reveal half of the things that it has not revealed so far. So this guy helps this guy, then it reveals half of his information, right? But now the other half is still secret. Now it helps this guy, it has to reveal half of what is secret so far. And now if you add all this, you get this. So you have to reveal half of the secret so far if you want to maintain the code MDS, meaning maintain Shamir scheme. So how did we prove this? So that's the second takeaway, that separation is actually pretty bad. But maybe you want to use it because this is what's there and it's easy to construct. So it depends on the system. Now, how did we prove this? So it turns out, so let's take this example. So I'm moving from the 4-2 example to a 5-3 example, and L equal to 2. So L is less than K here. And let's suppose this guy fails. And so 1 prime, yeah, so these two guys fail, these two share, and I'm trying to repair them by connecting to other nodes in the system, right? And let's focus on what this guy sends to this guy. So what 2 sends to 1 prime, so let's suppose it's a subspace S1, and what 2 sends to 5 prime, let's say subspace S2, right? So it's revealing, I'm thinking linear schemes. So I'm revealing two subspaces, which are S1 and S2, right? And if you want to minimize the observation of these two guys, you have to make these subspaces overlap, right? Because it observes the direct sum of these two, or the sum of these subspaces. I mean, in the worst case, assume, the best case is that S2 is equal to S1. So you're just revealing S1, basically, right? But it turns out if you cannot make them overlap too much, because if you make them overlap too much, then the scheme is not MDS anymore. It's not Shamir scheme anymore. So there's this trade-off, is that I want them to overlap, but till the point that the scheme is still MDS. And it turns out this imposes some constraint, some geometrical constraint on the intersection of these subspaces. And this is the expression of this intersection. So if you want the scheme to be MDS, then you have, these subspaces have to intersect that much. They cannot intersect more because the scheme is not MDS anymore. That's the high-level intuition of it. And the way to prove it actually borrows from the theory of interference alignment. And basically, you have to write down the condition on the subspaces. What does it mean for this guy to repair this guy? So some subspaces should align. And then you write these conditions. And unfortunately, I don't have an intuitive proof. The proof is by induction, so which is not my favorite type of proofs. But you can prove that every two subspaces have to intersect in half of their dimensions. And the way to do it, and then the ingredients in the proof, you get these conditions from the interference alignment. Okay, how much time do I still have?
Let's say, yeah, about 15 minutes.
Okay. So again, so the second takeaway is that separation can be bad because the secret size can decrease exponentially with the number of parties that can collude. Okay. So this kind of concludes the first part. Yes.
Is it without loss of generality that the scheme is linear, that you're doing subspaces, or?
So we haven't looked at nonlinear because actually on purpose, because we tried to look at it a little bit and it's very hard. And the motivation was, let's see what we can do with Shamir's scheme, which is linear, which is already linear. I think my co-author might have presented something on nonlinearity. Shri Kuparaju, he's a postdoc at UCSD now, and Asil Omar, but I'm not sure. Things are much easier when they are linear. So here also, so I'm going to skip the open problems because I want to move to the new stuff that I've been working on a little bit, which is how to deliver a secret. And what do I mean by delivering a secret? So let me, again, give you an example. So if you couldn't follow, you can start following now again. So this can be standalone also section. So now forget about repair. So everything is nice. There's nothing failing, nothing repairing, nothing being repaired. But now I'm looking at the communication cost of delivering the secret to the user. So I have a secret sharing scheme, and the question is, how much this guy should download to know S? Well, if he connects in this 4-2 scheme, if he connects to 2, he can download 2 shares and decode. But is this necessary? And the intuition, this might not be necessary because here we are insisting on decoding S and decoding the key. And let me show you an example. So if the user connects to more nodes, more shares, turns out he can decode the secret by downloading less. And this is the example. So this is a 4-2 secret sharing scheme such that if you connect to any 2, you can decode the secret, but you have to download 2 shares. But if you connect to 3, you can still decode the secret, but you have to download to 1.5. I apologize for the decimal point.
Sorry, I
Yeah.
came late, so I
Yeah.
know the people who asked to forget it.
Yeah, sure, yeah.
Explain what's going on here.
Yeah, but first, was the problem...
It's not-
Oh, okay. So I have, are you familiar with secret sharing?
Yes.
Okay. So I want to deliver the secret to the user, and I care about how many bits I should download from the system. I'm thinking of these as stored in the distributed storage system, right? So this guy, if you think of these 2 as 1 unit, right? He has to download 2 units, which is first unit is S plus K and S plus 2K, or any of these 2, right? And he can decode. And the question is this 2 units necessary to decode? And why it's even an interesting question, or what's the motivation? The motivation is that the user here, it's true that he decodes S, but he's decoding the key, and maybe he doesn't need the key. And maybe if you say, well, I don't care if I'm obtaining the key, maybe I can save on download, on communication costs, right? So that's the motivation. Now, can I do it? And this is I'm going to give you next an example where, to give you some hope that this is an interesting question, actually. You can do it by downloading less. And this is the scheme. Okay? So now, still, if you talk to any 2 shares, you're going to be able to decode the secret, right? But let's see if this guy talks to 3 shares, he's going to download only 1 part of each share and decode the secret, which is now, the secret is 2 parts, S1, S2, and 1 of the keys. So basically, he's not downloading all the keys, but only part of the keys. So it's similar to the repair in distributed storage, if you know what that is. If you don't know, you can just think of it as a standalone problem. Okay? Of course, the code here is a little bit more complicated to allow this flexibility. So if a user contacts 2, he'd have to download actually 4 symbols. If a user contacts 3, he downloads only 3 symbols. And the natural question is here, how much the user should download, given that he contacts a certain number of nodes, and can I have, and this is the main question I want to answer, is that can I have a code that can allow optimal communication cost for any user contacting any number? Yeah.
Storing S2 plus K2 in node 2.
Oh, because this guy may contact these 3. So he has to download this, maybe.
Okay, so for any choice.
Yeah, any choice, yes. Yes.
This, so it's different from distributed, I mean, the reality of distributed
scared using the TDB being prepared more than it's. So if you
Yeah. Exactly. Yeah. There's an analogy. So actually, I have a backup slide on this, but yeah, the motivation for this is well. Let me give you the motivation. So this problem was. So this is the third takeaway. So if you're happy with 3 takeaways, that's it for today. Is that the third takeaway is actually a user in the secret sharing problem. If you're happy the user only decoding the secret and you don't care about the keys, then you can share. You can save on the communication cost, right? So now, how much you can share? That's the question. How much you can save? So this problem was posed by Langberg, Cleaver, and Brook, and they characterized the. Actually, it's an upper bound on how much how big is this? How much you should download to decode the secret. Suppose, given that you contact D nodes. So remember, K minus L is what Shamir's gives you, and actually you can save this factor if you contact more nodes. Now, the way it was proved in this paper was information theoretic, but like Vijay said, so actually this is where we saw the connections, that we thought, well, this problem is very connected to distributed storage, and basically the high idea is that you can think of the user as repairing a share that does not exist, a fictitious share. I won't talk more about this, but that's the trick. And then you get the same bound. Now, but it turns out that this is an easier problem than storage, and I can tell you more about it offline. Because actually we can construct exact regenerating code for that is universal and it's much more tractable than storage because you're only repairing one share basically. But anyway, so what they showed, yes.
So you're holding the fact that you need to have K minus L fixed when you just contact the minimum number. That's the one fix. So you're trying to map.
Oh yeah, exactly. Yes.
You hold that fixed and you see what.
Yes, exactly, yeah. So I want NKL to be always yes. Yeah. So I want a scheme that guarantees whatever Shamir guarantees plus something else, right? Now, what is this something else? Either you say, well, I want also a user that contacts 10 more to be optimal. And that's what actually the origin paper gave a code that either you contact K to get the secret or everything or N. And what I want to talk about is that it actually can construct a code that is guarantee whatever Shamir's scheme guarantees plus it is optimal for any number of nodes that the user contacts. So it has some universality property. Okay? And we call these staircase code. The main idea is actually inspired by Vijay's code, product matrix code, is that instead of doing what classical information coding theory does, you multiply the generator matrix by a vector, your information in the vector, you put your information in the matrix, but you design this matrix very carefully to get the properties that you want. So this is my message here. This is the secret, and these are the keys. And the matrix has this staircase property where you put zeros. And these zeros are giving you some sparsity that's going to help you in decoding without having to download too much if you happen to decode contact too many nodes. Again, I'm not expecting even for you to be able to follow the details why I'm doing this thing, but just want to convey the idea. And I'll convey the idea maybe in an example. But basically, if you want to build this kind of staircase code that are universal in minimizing communication cost, if you go back to the first slide, we had the Vandermonde matrix times a vector. Here I have Vandermonde matrix times this matrix, where I'm carefully filling this matrix with keys and messages, and it has some redundancy. So here, basically here, the same keys are used here in this column. So there are lots of redundancy and lots of zeros placed in the strategic places to achieve that property. So this is the example for the 4-2. Oh, so again, so this is the 4-2 example that I started with at the first slide. So I want, if you contact 2 to be optimal on download, on communication cost, meaning you have to download everything. If you contact 3, and even if you contact 4, I want you to always be able to get the secret by obtaining the minimum, by using minimum communication cost. And this is the matrix. So this is what I meant by, where is it? Yeah. So here's how we design. So the S's are your secret, the K's are your keys, and you see like there are K1 that is used again here, K2, K3 used here, K3 is used here, and there are zeros here. So the recipe for this matrix is in the paper. It's on arXiv already, but let's check it really quickly that how is this done. So suppose a user contacts 2 parties, how can he decode? So first, so basically, if you contact 2, you have to download everything. If you contact 3, you download the blue and the red. If you contact the 4, you only download the blue. And if you count those things, you see that you match the bound. Now, why you can decode, so first, the user that contacts 2, he downloads everything. And then using these guys, you see the zeros are placed such that he can decode these. So he can decode S3, S6, K3, K4, K5, and 6. And then what he does some peeling. So then he removes these things from the previous parts of the shares and then decode again and again. And then for a user that contacts 3, he forgets about these shares. He doesn't download them. He only download the blue and the red, and he can do the same thing again. So here you have the right amount of zeros to allow him to decode from 3, and then once he decodes them, he cancels them out, and then he can decode again. So, and that's the basic idea of these codes that we call staircase codes. So this brings me to the, yes?
If you look at the same kind of how much you reduce the communication, but also how much you increase the storage per
Oh, no, here it's the same amount of storage.
Well, they used to, for the Shamir scheme, they only have to share one key and one secret, right? Here you split it into 6 units.
But each unit is 1/6. So in terms of storage, think of it as I'm storing the same amount of storage.
So your storage is the information you store and not the actual storage then? Because
No, it's actual storage, yeah.
So,
So think of it as think of it as 1 megabyte, right? Either you think of 1 megabyte as a big symbol and use Shamir scheme, or I divide the 1 megabyte into 6 equal parts, and this is what I do. So this is more, they're paying more in computation complexity. So this is still 1 megabyte, or 1 terabyte, whatever you want. But I'm dividing it into smaller pieces, and I'm coding on these pieces. Okay. So some open problems relate to this problem problem that I talked about how to deliver a secret. First, that my student is working on how to generalize this to secret sharing code that are not threshold secret sharing code, that have general based on general access structures. And another interesting problem, we always assume that the dealer has direct connection to the parties. Maybe he does not have direct connection to the parties or the shares. Maybe it connects to them through a network. And there are interesting problems that happen that the group of Kannan Ramachandran has worked on a little bit. And also, you can also ask the question of, what if I want a secret sharing scheme that can minimize communication cost to the user, but also you can repair at the same time? So can we do these things? So this kind of concludes my talk.